Okay, at the end of the practice problems, the last video, just ran out of time at the final answer, so I'm not sure if it got on there or not. But it was question number 16, and the final answer was 13.714 centimeters, okay, for the focal length. All right, a few little finish your upper things, like reminders or solidifying, or if we were actually in a classroom, it would be me saying, okay, did you figure this out? So when we're talking about converging devices, optical devices, we have two options. There is the concave mirror and the convex lens. Each of these have 5 cases. Each of these have an F that's positive. The only time you can get a virtual image from these, wow, that's really blurry. The only time you can get a virtual image from these is if the object is placed between F and the mirror, and the virtual image is always, always, always larger. Okay, those are converging devices. Converging because rays going in parallel to the principal axis when they hit, whether it's a mirror or a lens. Whoops, I better make this a lens since I made it pass through. Will converge at F on the opposite side. And if it was a mirror going in parallel to the principal axis, they would reflect so that they go through F on this side. For lenses, the real side is the opposite side. For mirrors, the real side is the same side as the object. So this is the object here, okay? Those are converging devices, and so the F is always positive. For diverging devices, the options are a convex mirror and a concave lens. Okay, they're called diverging because, since I did the lens first up there, rays going in parallel to the principal axis will get refracted in such a way that if you were to follow them back, they would look like they were coming from F on the same side of the mirror as the object. Because it's on this, remember the opposite side is real. So because of that, the F is always negative for a diverging device. Okay, same idea for a mirror. A ray going in parallel to the principal axis will get reflected in such a way that if you were to follow it back, it would look like it was coming from F on the opposite side of the mirror, which this side is the virtual side, and this side is the virtual side. So the F always for convex mirrors and concave lenses are negative. Diverging, you have to follow the refracted or the reflected rays back to see where they're going to cross, and they'll cross at F. The dotted lines mean I'm actually following them back, they're not really there. Whereas up here, they really, honest to goodness, do cross at F. Okay, they really cross, and so this is the real side, okay? There's a couple of issues with the lenses, just one that we talked about with mirrors, which was called spherical aberration, and spherical aberration happens with lenses as well. So if you have a convex lens, rays going in parallel to the principal axis should get reflected through F on the opposite side of the lens. But if you remember with mirrors, the problem was, sorry, it's shaking again. The problem was if they went on the outer edges, if they used the outer part of the mirror, that they didn't quite make it through F. And the same is true for lenses. So how do you fix it? You fix it by only using the middle section of the lens. Okay, if you use only the middle section of the lens, then they'll cross through F. If you don't, if you use the outer ridges, then the image you're going to get is going to be a little bit blurry. Okay, and the ones that are crossing on the outer edges, if you remember, they cross before the F instead of at the F. Okay, so spherical aberration is for both lenses and mirrors. The other one that's only for lenses is called chromatic aberration. And if you took biology, then you probably know what the chrome part means. It's from chromoplasts in plant leaves. Remember, there were chloroplasts and chromoplasts, and the chloroplasts were what gave the green color to leaves. And when the frost comes in the fall and it kills the chloroplasts, then what you're left with are all these beautiful colored leaves. Chromo means color. So chromatic aberration results from when a white light ray, and most of our light is white, strikes a lens which is made of glass or plastic. All of the colors travel the same speed in air, but when they enter the glass or plastic, they all travel at different speeds. And because they all travel at different speeds, they all get bent a different amount. Remember, the index of refraction was the speed of light in a vacuum over the speed in the other material. So if they all travel at a different speed in the glass or plastic, they're all going to have different ends. And who cares? We care because remember, how much they get bent by is based on Snell's law. N1 sine theta 1 is equal to N2 sine theta 2. So they all have the same N1 in air. They all hit the surface at the same angle of incidence, but if they all have a different N2 inside the lens, then they're all going to have a different theta 2. And so what that means is that when the light comes out of the lens, it can come out with all the different colors not at the same spot. And so when you get your image here, it's going to have like a fringe of color around it. Okay? And that's what chromatic aberration is. So it's a fringe of color around the image as a result of the white light being separated into its different colors inside the lens. Okay? How do you fix it? Well, really, the only way to really fix it is to put like if this is a convex lens, then to put a concave one right after it to try to put the light back together into its colors. I'll put all of its colors back together into white. Okay? So you can cancel it out by using a diverging lens here. All right, so that's called chromatic aberration. All right, the one other piece that I wanted to talk about is something that we use a fair bit in our lives, and it's called a double lens system. A double lens system. As its name implies, it has two lenses. Now, where would you find this? Well, maybe in a microscope, maybe in a telescope. There's all kinds of places. Okay, so you have one lens, and if this was a microscope, one lens would be the eyepiece, and then the other lens would be the one down at the bottom, you know, where you turn it on the base. I think it's called the ocular lens. So you have two lenses. We'll call this one number 1, and we're going to run out of time, so I'll have to start the next video in a minute. And so F1 and F2 would be different. They wouldn't have to be the same. And there's some distance apart. Let's say they're 40 centimeters apart. Okay, and so this guy has an F and a 2F. All right, and so does, and in here would be the same, and then this one an F and a 2F. Okay, and I'm just not putting the F's and 2F's in here because it's going to be too confusing. So let's do an example. Let's put our object here, and we'll say our DO1, the first object. Let's say it's 6 centimeters from the first lens. And we'll say our F1, oh no, okay, sorry. Let's make this one 8 centimeters and make this 6 centimeters. Okay,